So in this lecture, we're going to have some kind of odds and ends, some kind of strange things here. They don't really have a different place to talk about. So we're going to talk about Riemann-Stieltjes integrals. So I have a little function little f on AB and a function capital F on AB. So we're going to say the capital F is non-decreasing and continuous from the right. So capital F does not have to be continuous, but we are going to make the stipulation that it's continuous from the right. That's not particularly necessary, but it's a very common assumption when you're in this setting talking about Riemann-Stieltjes integrals. But little f, I'm going to assume is continuous. And there's no connection between capital F and little f. So in the previous lectures, capital F was often an antiderivative of little f, but here, there's no connection between the two. These are two completely independent functions. Okay? So we know about how to do Riemann sums. Right? Well, we want to do some Riemann-Stieltjes sums. Okay? So recall the definitions of the upper and lower Riemann sums. And remember, for a continuous function, if we wanted to approach the integral, it didn't really matter if we used the upper sum or the lower sum, as long as the mesh of the partition was small enough. Meaning, as long as all of the points in the partition are close enough together, then it doesn't matter how I define the upper or lower Riemann sum or a Riemann sum with respect to some sampling. I'm going to be close to the integral. And the same is true here. So here, so we have a partition of AB, so x0, x1, x2, they're increasing, and x0 is A and xn is B. We have a sample, S1 up to Sn, of AB with respect to this partition P. If you remember, a sample means Si is, I just pick a point from each interval in the partition. So that's what a sample means. So I have a partition, and a sample is I just pick any point from the partition. And I can define Riemann-Stieltjes sum of this function with respect to the integrator, capital F. So here I'm calling the capital F the integrator. And I define the sum this way. So I can think about this as being like a weighted Riemann sum. So because my capital F is non-decreasing, that means each of these differences here is non-negative. And these capital F of xi minus capital F of xi minus 1 are acting like weights. Okay, so I'm multiplying these function values at the sampling points, Si, by these weights, and then I'm adding them together. Right? So notice that this looks a lot like the usual Riemann sum. So this is a Riemann-Stieltjes sum. So the fact that this is capital F is the thing that makes this a Riemann-Stieltjes sum. So let's compare this to just a regular Riemann sum, xi minus 1. So this is a usual Riemann sum. Okay. Here the difference is instead of xi minus 1, then here I have capital F of xi minus capital F of xi minus 1. So here I could think about these as being weights. Right? So I want to take this point and I want to apply a weight to it, and the weight is the length of this interval. So here we can think about interpreting the Riemann sum as a weighted sum. This is also a weighted sum, but this capital F gives me some flexibility for how I want to weight things. Right? So if this capital F minus capital F of xi minus capital F of xi minus 1 is large, then I get a big weight here, which means I'm considering the Si that goes along with the intervals in the partition where this difference is big. I'm giving those a big weight. I'm considering them more important in the weighted sum. If this is small, then I'm kind of de-emphasizing it in the sum. Okay? So let's see. So as I mentioned up here, if this capital F of x is just x, then this becomes exactly the usual Riemann sum. Okay? So the usual Riemann sums are a specific kind of Riemann-Stieltjes sum. Okay? So we can define upper and lower Riemann-Stieltjes sums and Riemann-Stieltjes integrability by if the upper sums and the lower sums converge to the same value, etc. So we can define a Riemann-Stieltjes integral. Riemann-Stieltjes integral is, we denote it like this. So I'm going to say df of x. And so the d capital F of x makes sense because here it's a difference, right? So the d here stands for difference. Okay. So we can see kind of the relationship between this and this. We're not going to do much with this, but we are going to look at a few specific examples. So this example is one that shows us kind of the usefulness of Riemann-Stieltjes integrals as opposed to just the usual Riemann integrals. So why would we care about something like this? And if you've done any statistics, which I highly recommend, you will probably recognize this as expectations with respect to some random variable whose CDF is equal to this capital F. Okay? So if you notice the conditions that I put in capital F, it's non-decreasing and right continuous. Those sound a lot like conditions that we put on the CDF of a random variable. So if you don't know what those things mean, I highly recommend looking into some probability and statistics because those are very useful, but they're not important for this class. So let's take a partition and a sample. Right, so here, my capital F is 0 to the left of C. So C is some fixed point between A and B. Capital F is going to be 0 to the left of that and 1 to the right of that. Okay, so I have capital F looks like this. And now I want to pick a partition of my interval AB and a sample. Right, so I'm going to split my interval up into these pieces. And now I'm going to do this weighted sum of values of little f. So little f is still our continuous function defined on AB. Right? So now, if I take 2 points over here, so like x1 and x2, capital F is 0 at both of these points. Okay? So that means that capital F of x1 minus capital F, x2 minus x1 is 0 minus 0. Okay? So f is not changing at all over here. So these differences are all going to be 0 minus 0 over here. Okay? So that means that so let's see, let's look at this xi minus 1 and then xi. Okay? So at some point in our partition, we have to go past C. Right? So the partition goes from A to B, C is somewhere in between. So at some point, our partition points are going to have C in the middle of them, or possibly exactly equal to. So I'll leave you to figure out what happens if it's exactly equal to. Well, that's included here. And so, so everything before that has 0 minus 0 here. At this one, I have a 1 minus 0, so the weight attached to this particular interval in the partition is 1. It's this value minus that one, which is 1 minus 0. And then again, over here, f is not changing, so I have 1 minus 1. So here I have 0 minus 0. Those don't matter in the sum. Here I have 1 minus 1. Those don't matter in the sum. All I have is f of si for that 1 point here times this difference, which is 1. So here si is going to be some point in between xi minus 1 and xi. Okay. So if the mesh of this partition is small, meaning if all of these x points are very close together, then si has to be in the same partition as c. Right? So c is in this interval of the partition, and si is also in there. And if little f is a continuous function, then f of si is going to be very close to f of c. Okay? And as my partition shrinks, this is going to become exact. So I've written here, as the mesh of the partition goes to 0, f of si, where si is the sample point in the same interval as c, those are going to get closer and closer to c. Okay? So in this case, the Riemann-Stieltjes integral is going to be just little f of c. Okay? So my any Riemann-Stieltjes sum is going to be one of these, and si is going to get closer and closer to c as the size of the intervals shrinks. And so I get this. So here, let's interpret this again. So we said this capital F is kind of giving weight, right? So this is like a weighted sum. Here, the purpose of this kind of jump discontinuity is to apply all of the weight at c. So the weight is given by the difference. Okay? So what this capital F does is it essentially just applies all of the weight to the point C, and then we have this kind of this result. So if you know about CDFs, you should be able to interpret this and make this understandable in terms of some random variables. If you don't know about random variables, well, I highly recommend looking into them because probability statistics are some of the most applicable and beautiful areas of math. So well, feel free to look into it, but we don't need it for this class. Okay. So this capital F having this discontinuity here allows us to have basically a weighted average of the function to the left, and 100% of the weight is at the